Okay, so we'll look at, we'll continue looking at some parametric bootstrap. So using, again, the idea behind statistical computing or computational statistics is that we can answer some difficult questions about probability and statistics through simulation, having the computer as a tool to kind of do the legwork or the grunt work behind estimating certain parameter values and things like that. So on Monday, we covered estimating the mean and variance of the absolute value between x1 and x2, and we saw that we could get that analytically, but I think the computational method also made it quite easy. We looked at estimating the mean squared error of the trimmed mean, and we also did some empirical calculations of type 1 error rate in hypothesis testing. Okay, and so these are all examples of parametric bootstrap. We'll take another look at parametric bootstrap, and I think this one's a fairly important example, and it's all on power calculations. Okay, so I guess this will be a review from your intro statistics class, but we have type 1 error and we have type 2 error. Okay, type 1 error is the event where we have rejected the null hypothesis, but the null hypothesis is true. And type 2 error is when we have not rejected the null hypothesis and the null hypothesis is false. All right, so we assign the probabilities of each of these errors to the quantity alpha for type 1 error, and the quantity beta is the probability of a type 2 error. So power, we have another quantity that's of interest to us, and this is called power, and that's 1 minus beta. Anytime you do 1 minus, it's the probability of not that thing, the complement. So it's the probability of not committing a type 2 error, which when translated back would be the probability of correctly rejecting the null hypothesis when the alternative is true. Okay, so we'll take a look at an example here. Well, I just want to make sure everyone's comfortable with type 1, type 2 error, and all of this stuff from our intro stats and whatnot. Okay. Okay, so have you guys learned power calculations already in any other classes? No. Okay. So power depends on a bunch of things. Okay. So one of the things power depends on is the difference between the reality and the null hypothesis. Okay. So for example, the null hypothesis could be that the mean is 0. Okay, your null is whatever. The mean of something is 0, but in reality, the mean is 1,000. Okay, and if you have a fairly small standard deviation, like a standard deviation of say 100 or something like that, then it should be very easy to detect the difference, and any amount of data, even a small amount of data, should be able to say, oh, actually this should not be mu 0. In reality, let me just write this. Actually, I'm just going to write mu is equal to this. Okay. So in reality, if the mean is 1,000, then it should be easy to detect this difference. Okay. So in this case, your power will be very high. In another situation, you could have the null hypothesis is that the mean is 1,000, but in reality, the mean is 1,001. Okay, so in this case, is the null hypothesis wrong? yes, the null hypothesis is wrong because the reality is that the mean is 1001. So we should be able to reject the null hypothesis at some point in time. But in order to detect the difference between this and this, we would need a lot of data, right? So if we were using the same amount of data over here as we are over here, the power of this test is going to be much lower. We're not going to be able to, most of the time we won't reject the null hypothesis, okay, which means we are committing a type 2 error in that we have not rejected the null when indeed the null is wrong because the mu of the population is actually 1001, okay? But the question is this distinction important? If someone says the mean is 1,000, but in reality it's 1,001, is it important that we detect that difference? Maybe, maybe not, okay? And so when we're talking about power, a lot in other courses you'll learn kind of the formal power calculations. Here we're just going to get estimates using the computer. You know, your power calculations are going to depend on several things. One being the difference between reality and the null hypothesis, and other things would be how much data you want to collect, and also your alpha, your significance level, how willing you are to make a type 1 error, all of these things. If you're more willing to make type 1 error, you can increase the power of your test, but that comes with the side effect of making type 1 error more often. Okay, so we're going to do a few calculations here with Bootstrap. Okay, let me just okay, and so in this scenario, we're going to say the null hypothesis is that the mean is 1,000. Okay, and we're going to try out. We're going to do some power calculations with a few different alternative hypotheses. So one, we're going to have the alternative being 1,010. We can have the I guess not the alternative, but the reality being 1,100 and the reality being 1,200. Okay, so this is where the data is actually coming from. In all of these, we'll set the standard deviation equal to 100. All of these we can kind of modify and see how this affects our power. And then we'll take sample sizes of 20, and we can see how increasing the sample size changes our power or whatnot. And then to get our estimate, we're going to do 5,000 replications here. Okay? So I'll post all of this code up, but we'll say we're going to take samples of size 20. Our mean of the null hypothesis is 1,000. We're going to set the standard deviation of our distribution to be 100. We're going to do 5,000 replications, and then we're going to have the alternative hypothesis, or this will be kind of the true mean of the population. Okay, so the true mean of the population will be 1,010, and I'm going to create a function that's going to calculate the p-value of a t-test that we run. Okay, so we're going to assume so we're going to generate 20 random values from the normal distribution centered at 1,010 with a standard deviation of 100. Okay, and then taking those values, those 20 values that we've generated here, we're going to run a t-test with x, and then the null hypothesis will be that mu is equal to 1,000 here, mu 0. Okay, and then we're just going to say, give me back the p-value. Is that okay? So I can execute this function here. All right, and I just say, give me the p-value of, if I take a sample of 20, my null hypothesis is that it's 1,000, but in reality it's 1,010, and I have a standard deviation of 100. Okay, so in this case, it runs it, it calculates a p-value of 0.89. So we would not reject the null hypothesis in this scenario. Okay. All right. So I'm going to run this. So saying the alternative hypothesis is 1010. I'm going to run 5,000 replications. Okay. So I'm just going to say replicate, and we're going to just run this this command right here. So run it 5,000 times. It's already done. Okay. So if I just do p underscore value is 1, and we look at the first 10, okay, we see we get, you know, p-value of 0.88, p-value of 0.55, or 50, or whatever. I can just see how often would I reject the null hypothesis. Okay, so I would reject the null hypothesis about 7% of the time. So my power is quite low in this scenario. I have a power of about 7%, meaning my data led me to reject the null hypothesis only about 7% of the time, even though the null hypothesis is wrong, because the null hypothesis says it's 1,000, and in reality it's coming from an alternative, a population where the mean is 1,010. Okay, we can see how our power would be affected if we chose 1,050. If the reality was that the mean is 1,050, and that's what's generating our data, we can see how often we would reject the null hypothesis. Okay, so I'm just going to run these commands right here. Run the replications using our p-value function. Okay, and here we can see an increase in our power. Okay, if the data are coming from a distribution where the mean is 1,050, we end up rejecting the null hypothesis quite more often. Okay, and we reject the null hypothesis about 56% of the time. Okay, this is not incredibly high power, but we can see what's happening. I'm gonna and then let me just change the reality situation again. This time our data is going to be generated from with a mean of 1,100, and we're going to do the same thing. Generate data with a mean of 1,100. See how often we reject the null hypothesis. Okay, and here we see if the reality is 1,100, we end up rejecting the null hypothesis almost 99% of the time. Okay, so here our power is very strong. Okay, and that's because the difference between the reality and the null hypothesis are getting bigger and bigger, and so it becomes easier and easier to detect that difference. Okay, we can see how changing our sample size n would also increase or decrease power. Okay, so here let's just say we'll go back to our null hypothesis, saying that the difference between the reality and the null hypothesis is that there's only a difference of 10. Okay, we're going to still keep our standard deviation of 100, but this time we'll try different sample sizes. Okay, so basically I'll copy all of this again. Okay, and so for each of these, I'm just going to change the sample size from 20. So we'll start off at 20, and then we'll go up to 50. We'll go up to 100, and then 200, and we'll see how this affects everything. Okay. Okay, so generating this, yeah, we're still getting so when we do n around 20, we get a power of around 7%. Taking a larger sample size, okay, so we still have the same alternate reality, or the same real situation in that the data is being generated from with a mean of 1010. All I'm doing is now increasing the amount of data I'm collecting. So if I take 50, sample sizes of 50, we see my power increases, okay, 2.11. If I take more samples, larger samples, samples of 100, okay, my power increases even more. And at with samples of 200, you know, my power is up at 0.2844. So increasing the sample size, so here I'm taking sample sizes, you know, 10 times bigger, but my power has only increased not a ton, okay? So, you know, how big of a sample size do we need to go? You know, we can kind of guess and check and just see what, you know, samples of 2,000, and this takes much longer to compute, but we can see how this affects, you know. Maybe 2,000 is too expensive to do, so, you know, maybe we'll just try 1,000. Can I get away with half that amount of data? Okay, 1,000. Okay, and we can see, okay, that's not as good, 88 or something, and maybe there's something in between in terms of getting the desired power, okay? And so you could see when the difference between the null hypothesis and the real situation is small. In this case, there's only a difference of 10 units, and the standard deviation is 100. Okay, you can see you need quite a large sample. Okay, in an experiment, if you take experimental design, which I think is 101B, you'll learn the formal power calculations and all of that, which say, you know, if you want this desired power and you're expecting these kinds of things, this is the sample size you need to take. But here's kind of a like a hack method where hack in the kind of the derogatory sense, in that you know, you don't have to understand the math, you don't have to be able to do those calculations. You can just kind of ask the computer, let's try this over and over again and just see how often we're right or wrong. And I think this is the real power behind computational statistics, because as you get into these crazier and crazier situations, the probability and the math behind it they get messy, and this is kind of a nice way to get good high quality estimates without having to do all of these calculations here. Okay, so anyway, I also wanted to kind of do the analytic method in terms, so we'll see if we can get something in this vicinity of 0.5646 here for this second example here. So we're taking samples of size 20. We're going to have an alternative reality. Whoops. You know, something in this vicinity where the data is being generated from with a mean of 1,050, and we're going to see how often do we reject the null hypothesis. Okay, so I wanted to show you this calculation here. Okay, so and I hope you can see how this works here. Okay, so the null hypothesis states that the mean is equal to 1,000. Okay, and we're taking we've got a sigma of 100, and we're taking sample sizes of 20. Okay, so with the central limit theorem, we're going to say that x bar states that x bar comes from the normal distribution with what properties? Where the mean is 1,000 and the standard deviation is going to be 100 over the square root of 20, right? Okay, and if we're using a non-directional alternative, mu is not equal to 1,000. Okay, when do we reject? Okay, so we reject when our p-value is less than alpha, so we'll say alpha is equal to 0.05. All right, so under the, if the null hypothesis is true, okay, we are centered at 1,000, okay, and basically, if we end up somewhere out here, or if we end up out here, such that our tail has, 0.025 or 0.025, okay, this is where we reject, okay? So if our test statistic is over here, this we call our rejection region, and this over here is also our rejection region. Okay, and if our test statistic ends up anywhere in here, this would be our non-rejection region. Does that make sense to everybody? Okay, so let's try to figure out where our rejection region is. Okay, so what does this have to be? So basically, this is what we've got. So I'm gonna basically my z-score has to be equal to 1.96 or higher. And then over here I've got 1.96 or lower, right? Okay. But there is a problem in that when I conduct my test, I'm performing a t-test because I don't actually know that sigma is 100, right? So, because I'm looking at my data. So, essentially, because we know sigma is 100, we can do this. But when we look at the data, we're going to have to say x bar comes from a t-distribution with mean 100, standard deviation s over the square root of 20, okay, and degrees of freedom equal to 19, okay. But we're kind of we're going to kind of ballpark this with estimates of 100, okay. So anyway, what? Oh, negative 1.96. Yeah, yeah. Okay. But we'll just keep it easy. We'll do it like this. Okay. So my z is 1.96. So if I use 1.96 is equal to basically x bar minus 1,000 over 100 over the square root of 20. Okay. I can figure out that x bar should be plus 1,000, and this gives me, what is this? Times 100 divided by okay, so I get 1,043.827. Okay, so over here, I reject at 1,043.83, and over here I would reject at basically 1,000 minus this. Where's my negative button? Okay, 956.17. Sorry. So this is Is this okay with everybody? Or how I'm getting these boundaries of the rejection region? Okay, so I have these boundaries, 956.17 and 143.83. Okay, and so for our power calculations, okay, we're going to say the reality is that the alternative comes from, is that mu is equal to 1050. Okay, and so in our situation, okay, we're at 1050, and what is our rejection region? Our rejection region from the previous page was, I already forgot, 956.17 and 1043.83. So 956.17, 1048.13. Okay, and so if we end up over here, we reject, and if we end up over here, we also reject. Okay. So with the central limit theorem, now we can say x bar comes from normal distribution with mean 1050 and standard deviation 100 over the square root of 20. Okay, and so we can see how often do we end up in our rejection region. Okay, so over here we would get z is equal to 1048.13 minus, or wait, am I doing, I think I have my 1043.83. I'm getting my numbers all wrong. This is 1043. 1043.83, is that what I said? I think. 1043, yeah. Okay. So 1043.83 minus 1050 divided by 100 over the square root of 20, and we get a z-score. And pretty much, I mean, we could calculate the z-score over here, but this is like super far away, so it's going to be like z is -7 or something really extreme. I don't know. Okay, so let's do this. 1043.83 minus 1050 divided by 100 over the square root of 20. Is that right? Okay, so I get z is equal to -0.276. Okay, and so we can find, what is the area to the right? So this is going to be 1 minus p norm -0.276, right? Okay, so let's see what r tells us. This is 1 minus p norm -0.276. Okay, so we get 0.608. -0.608. Okay, so this is 0.608. Okay, and so our power, our theoretic power, is equal to 0.608. I think our power is slightly reduced because we're using the t distribution. So we could do a calculation with the t distribution with 19 degrees of freedom. But we see that the estimates that R produces are in line with the power estimate. Let me see if let me do p norm, not p norm, pt, degrees of freedom equal to 19. Oh no, that's about the same. Okay, well, I guess not significantly different. But this is what our power calculations would look like. Okay, is this all right? Okay, so I'll this is kind of it's a little messy here, but anyway, So yeah, R can do this. We can simulate get a lot of these calculations, you know, rather easily. Okay. I wanted to do just another example of power for the Shapiro-Wilk test for normality. So this is a test where you can see if the data you have come from a normal distribution, and you can see how good is this test. Okay. So for example, if I generate 100 random data points, and look at a histogram, this is what it looks like. And then we ask, could this come from a normal distribution? Well, we can have R create kind of this kernel density estimate. And so this is, this is our histogram, and then when we turn it into a density, it does this to it, okay? Here, maybe I'll do breaks equals 20, just so you can kind of see. That might be too many. That's exactly the same as what we had before. Okay, well, anyway, we can do that, all right? And then, I can generate data from a non-normal distribution. It's going to look very similar. It's coming from a t distribution. All right. So let's see. Okay, so I get, t distribution with degrees of freedom equal to 3. I'm getting, one significant outlier out here, okay? And we create the density, and it looks like this, all right? So anyway, we can run the Shapiro-Wilk test, which basically you just do Shapiro test normal, and or whatever data it is. So remember, we stored our 100 random the 100 random data points generated from the normal distribution into just this vector called normal. So we run the Shapiro test on normal. It gives us a p-value of 30%, so we don't reject the null hypothesis, and we say we have no reason to doubt that this data could come from a normal distribution. Okay, and just like many of the other tests, if you store it as a value, you can get the you can write $ p-value and get its result right there. So so I'm going to try. I'm going to create a function here, and in this function, I'm not specifying anything here. All I'm doing, as far as arguments go, I'm just going to say when you run the function, generate 100 random data points from the t distribution with degrees of freedom equal to 3. Run the Shapiro-Wilk test on that data and give back the p-value. So if I just run the p-value once, that function once, it gives me a p-value of practically 0. Okay. Another example, another time I run it, it gives me a p-value of about 2%. Okay. And this is just data coming from a t distribution with degrees of freedom equal to 3. And so I can run this 5,000 times using the replicate function. Okay, it's done. And then we just ask, how often did you reject the null hypothesis if you're using 5% as your alpha? And it says, I rejected it 87% of the time. Okay, and we can see, so the t distribution ends up being the normal distribution with infinity degrees of freedom, right? So we can see how good is the Shapiro-Wilk test at distinguishing between the t distribution and the normal distribution if I increase my degrees of freedom. Okay, so all I have to do is just kind of mess around with this, and if I can say, let's use 5 degrees of freedom as my function to generate p-values. We're going to run this 5,000 times. Okay, and then so just the small switch from degrees of freedom 3 to 5 has a profound impact on the power of the test. Okay, so with 5 degrees of freedom, we're having a much more difficult time detecting, recognizing that this is not a normal distribution. Okay, I mean we still can, but with only about 57% of the time we're able to do it. Okay. Okay, and you could try other things. You can just say like, what if instead of the t distribution, I'm going to use something, just something crazy. Okay, like let's do like r beta, and we'll do 4 4. Okay, and so let me do 1,000 of these, and just so you can kind of see what this looks like. Okay, so this is a beta distribution with parameters 4 4. Okay, can we detect this if I have a sample size of if I have a sample size of 100, okay? And we can do this. And it says it actually has a hard time kind of telling the difference here with sample sizes of 100, okay, using beta 4 4. So anyway, as far as parametric bootstrap goes, we can use it as a way to get power estimates, see how often we would reject the null hypothesis if we were using a certain set of parameters between the null hypothesis and the reality situation and the alternative. And you can modify it in all sorts of ways, and because all you're doing is just replicating it over and over and over again, you don't have to worry about the math, but it will give you a very good estimate. So as long as you can just run a test and see what happens, you can kind of answer a lot of these more challenging questions without the need to worry about the complicated math side of it. Okay, so we'll end a little bit early, just a few minutes early here, but well, I guess before I let you go, are there any questions? Of course not, right? If I said we're going to end here, nobody's going to ask questions. Okay, all right, well, have a good weekend. We'll see you guys on Monday.